Yeah, so I'm also going to be talking about combo, and basically there isn't like a one specific topic, because I think that combo, especially later on in like computational competitions, doesn't have a lot of like set topics. So a lot of it is just like casework or kind of looking at clever observations and stuff like that. So we're going to be taking all of like the basics, which is like combinations and permutations and stuff, and then just doing problems based on that. Yeah, so this is the first one. We have 20-sided dice, and they're labeled 1 through 2020. And then Anne keeps a running sum of all of the dice rolls. And she's going to stop when this sum is greater than 2019. So we have these two numbers, x and y, that represent the most and least likely running sums that are stopped at. And we're asked for the ratio between the probabilities of stopping at these two values. So I think that for this problem, it might seem a little bit hard if you have to like find the probabilities of stopping at each sum and then find like the most and least likely and then find the ratio of those two. But what it comes down to is kind of just thinking about it like logically. The central observation is not like something that you need to do a lot of computation for, basically. So what we're going to notice is that the most likely, or actually the least likely, which is y, is going to be 4,039. So y is the one we're least likely to stop at. And 4,039, the way that we get this is we have faces 1 through 2020. And the only way that we can get this sum, or that we can stop at this sum, is if we previously had 2019 and then the last roll was 2020. Because anything else means that our sum, or our sum before we get this last one is going to be greater than 2019, which is not what we want. Okay, I don't think I explained that very well, but basically, intuitively, like 4,039 is going to be the least likely because we're getting a sum of at most 2019, and then the last roll is going to be at most 2020. So 2019 plus 2020 is the only way that we're going to get a running sum of 4,039 in the end. And then something kind of similar for the most likely one, which is x, is that x is actually 2020 itself. Because whatever running sum that we had before this, we always have some value that can make this total running sum that we stop at add up to 2020. So this isn't exactly like super formal, but I think that like the intuition kind of makes sense. And then after this is when we actually need to like think about how to calculate these probabilities. Okay. So for let's start with the probability of getting 20/20. So we're going to notice that I'm just going to put this formula first. So the probability that we stop, or the probability that we get some sum n at some point is equal to 1 plus 1 over 20/20 to the n minus 1 times 1 over 20/20. Okay. And this is true for n at most 20/20. So if you think about it, let's start with just n equals 1. The probability that we get a running sum of 1 at some point is just 1 over 20/20. And then the probability we get a 2 at some point is going to be the like 1 over 20/20 for we just get a 2 first. Or we can get a 1 and a 1, which is going to be 1 over 20/20 squared. And then you can imagine that for n equals k, we can get that value, k, at first, or we can get like 1 and then k minus 1, or 2 and then k minus 2, and so on, or up to k minus 1 and then 1, which is k minus 1 over 20/20 squared. Or we can split this into 3 things. And all of this is working because n is at most 20/20, which is the highest roll that we can get. So now we're actually going to use stars and bars. So if we want to like partition the sum of k into 3 rolls, where each roll is at least 1, we have k stars, I guess, and then 3 boxes, so 2 bars. And if we first just put like 1 into each of these boxes, because everything is at least 1, then we're left with k minus 3 stars. And then applying the formula, we have k minus 3 plus 2. Choose 2, which is k minus 1 choose 2. And then obviously we have to divide by 20/20 cubed. So this goes on until we get to like k minus 1 choose k minus 1 over 20/20 to the k, where basically we're always going to have, like, if we have m rolls that add up to k, then we have k minus m stars and then m minus 1 bars, which gives us k minus 1 choose m minus 1, all the way up to m equals k. Okay. And then this you might recognize as being 1 over 20/20 times 1 plus 1 over 20/20 to the k minus 1 power, just by binomial theorem. Okay, so that's like how you can get this formula. that is over here. And now we can find the probability that we get a running sum of 2020 is just going to be 1 plus 1 over 2020 to the 2019 times 1 over 2020. And then this is for X. And then for 4039 for Y, we need a running sum of 2019, and then we need to roll a 2020, which means that we can plug in 2019 for N here. So this, and then we multiply by 1 over 2020 for the probability that we roll that 2020 at the end. Okay, yeah, and then finding the ratio of these two, we just get 1 plus 1 over 2020 over 1 over 2020, which is 2021. Okay, so there's kind of two parts to this problem. The first one was like the observation about how we like get X and Y. And then the second part is using stars and bars to find this formula and then just plugging it in. Okay, feel free to ask any questions, but I'm going to move on now. Okay, so for this problem, we have 15 people, and then each person orders soup or salad with equal probability. And they're asking for the probability that the number of people who ordered soup is one more than the number of people who ordered salad. Yeah. So I said they order with equal probability. That was not correct. They can order like nothing, and they can also order both of them, but each thing that they order is ordered with probability 1/2. Sorry about that. Okay, so for this one, I guess just like to interpret the problem, we're going to have like 1/2 to the, let's say, I times 1/2 to the I plus 1, where the first product represents the probability that I people order salad, and then this is the probability that I plus 1 people, which is one more, order soup. And then we have 2015, choose I, 2015, choose I plus 1. Is this correct? I don't think this is correct. So we need to choose like these people who order salad and soup, but actually there's 2015 people regardless, so this is just 1/2 to the 2015. Okay, I think this looks right. 1/2 to the 20. This is still not right. 4030, because, okay, sorry about that. Each person has two choices. So 2 choices they have to make, which means 4 equal possibilities total. So 1/4 to the 2015 or 1/2 to the 4030. Okay, now that we have that out of the way. Yeah, so this problem, we can either try to just like leave these combinations as they are, or we can do a clever manipulation on them to make it easier to evaluate. So for this, I is going to go from 0 to 2014. And it's kind of annoying that we have like I in both of these, because if we had like something minus I in the bottom part and then something just I, like we're choosing something minus I and then we're choosing I from something, then we can multiply these and then get like a nice expression. So the way that we can get this to like this state is by doing 2015 choose I times 2015 choose 2015 minus I plus 1. And this is obviously equal. So if we write this out, we have 2015 choose I times 2015 choose 2014 minus I. So now we're choosing I plus 2014 minus I, things total. And each time we're choosing from 2015 things. And one way that we can think about this is that, let's say we have like 4,030 objects, and then we split this into 2015 and 2015. And out of these 4,030 in total, we want to choose 2014 things. But if we're summing over I equals 0 to 2014, for each of these I values, we're choosing like how many of the 2014 that we're getting from this first group, and then how many we're getting from the second group. So what this means is that if we sum up all of these products over I equals 0 to 2014, what we're going to get is just 4,030 choose 2014. Yeah, so this is kind of a common trick or manipulation that you can do. And then, of course, we have to divide by 2 to the 4,030, and then that's the answer. It's not like a numerical answer because they don't necessarily need one. You just have to find this expression. Okay. Sorry, got a little bit confused in the beginning, but hopefully everything makes sense now. Okay, we're gonna move on if no one has questions. Cool. Yeah, so for this question, we have a regular 21 gone, and we're looking at the set of line segments between any two vertices of this polygon. If we select two distinct line segments from this set randomly, we're finding the probability that they intersect. So if we have 21 points, 1, 2, 3, 4, 5, 6, 7. Okay. And then we're looking at the set of every single line segment between two of these vertices. Well, one thing we know is that if the two segments share a vertex like this, then obviously they intersect. So share a vertex means that they intersect. But if they don't share a vertex, let's say, oops, this one, and then this one, or we could do like this first one and then this new one. If the two segments don't have a shared vertex, then we're looking at something different. So when they don't share a vertex, there's going to be 4 points total. I think a better way to show this. Okay. So we have these 4 points. And if we're just looking at those 4 points, it doesn't really matter like where they are, it just matters the order that they're in. But the ways that we can connect these 4 in 2 pairs is like this, or like this. So we can see that there's like 3 different ways that we can connect these 4 points together, but exactly 1 out of the 3 have them intersect. So if the 2 segments that we choose don't share a vertex, that means that they intersect with probability 1/3. Yeah, so that was kind of the observation that pretty much finishes the problem after computation. So yeah, now we're just going to multiply stuff out. So the number of ways to select pairs of segments that do intersect or do share a vertex, is n choose 2 times n minus 2 choose 2 over 2. Because we need to choose 2 for the 2 vertices for the first segment and 2 for the second segment, but the order in which they're chosen doesn't matter. So that's going to give us like exactly this many intersections. And then for segments that do not share a vertex, actually, this is for segments that do share a vertex. Okay. If they share a vertex, there's 3 in total that we need to choose. So like if you look at this example, there's 1 that's shared and then 2 that we need to choose. So n ways to choose the shared vertex. And then just n minus 1 choose 2 to choose the other 2 vertices on the segments. Okay. Cool. So this is going to contribute this many intersections, and then this is going to contribute 1/3 of this many intersections. And we're taking everything over n choose 2 choose 2 because there's n choose 2 segments, and then we choose 2 of them, from S. Okay, so this is like not super interesting, but I guess we will just do the computation. So n is 21, which means that we have 21 times 20 times 19 over 2. And then all over n choose 2 is 210. So 210 times 209 over 2. And then we can just cancel some stuff out. So we don't need this 21 everywhere. And then there's like a 10. So what we're left with is 19 times 3 plus 2 over 209, which is 5 over 11. There's a 2 here. Okay. Cool. Does anyone have questions on this? No? Okay. I did not have time to put the last question in my whiteboard thing, so I'll do that really quickly now. But yeah, I've been writing some things wrong, so sorry about that. But hopefully, like, my corrections made sense. Okay, so the last question is from Math Prize, and it's about bags and marbles. So we have 2 bags, X and Y. One of them contains 5 marbles, 5 red marbles, and then the other one has 4 red marbles and 1 blue marble. And we're choosing one of the bags each time at random and removing a random marble from that bag. If this person repeats this step until one of the bags is empty, what is the probability that the blue marble is still in bag Y? So in order for the blue marble to still be in bag Y, like X has to be the one that became empty, which means that we took away 5 red marbles from X, and then at most 4 red from Y. But we did not take away the blue marble in Y. For this one, I think the most straightforward solution is just by casework, but there's kind of a pattern to it. So yeah, let's look at the cases. We either took 0, 1, 2, 3, or 4 red marbles from Y. So if there were 4 that were moved from Y, there are 8 choose 4 ways to order the marbles. And then we needed to choose y like 4 times, so 1 over 2 to the 4th. And then each time we're choosing a red marble, it's 4/5 times 3/4 times 2/3 times 1/2. Because at the beginning we have 5 marbles and then 4, 3, and 2 in Y, and then there's 4, 3, 2, and then 1 red marble in Y. So the total probability that we're going to get is 70 over 5 times 16, which is 7 over 8. If we have 3 marbles chosen from Y, this is like the same thing. So we need to choose 4/5 times 3/4 times 2/3, which gives us 2/5 probability that we get all these red marbles. And then as like before, if we had 3 marbles from Y chosen and then 5 from X chosen, we need the last one to be a red from X, because otherwise X would have been emptied already before this point. And then there's 4 red from X and 3 red from Y here. So that's how we get 7 choose 3 and 8 choose 4 here. And then we also need the 1 over 2 cubed to choose Y 3 times. So that gives us 7 over 4. So these are like not strict probabilities because we're taking into account that we need like 1 over 32 here from choosing X 5 times, but we can just multiply that in at the end. So yeah, this is like not something to freak out about because it's greater than 1. And then for 2, it's the same thing. So 6 choose 2 times 3 over 5 times 1 over 2 squared, which is 15 times 3 over 20, so 9 over 4. And then 1 is 5 choose 1, 4/5, 1/2, which is 2. And then 0 is just going to be 1. Okay. So adding up 7/8 plus 7/4 plus 9/4 plus 2 plus 1, and then times 1 over 32, we get 16 over 4, so this is 4, and then 7, so 7 times 9/8 over 32, which is 63 over 256. Okay, so for this problem, I think the casework is like not too hard to come up with because you know what needs to happen. Like we need to have the 5 from X and then some amount from Y. And then we have to be careful that when we're choosing these, the last one that is chosen is going to be the last red from X, because if it isn't, then we're not counting the case where like we just finished emptying X, and then the rest of it is just like normal probability stuff. Okay, that's the last problem that I had for today. Yeah, if there's any questions, please let me know. But a lot of these were kind of either like you need some specific observation by just playing around with stuff, or there's like some kind of common construction that happens. Yeah, that's it. We're kind of done early today, but you can stay behind if you have any questions. And then thank you, Ashley, for the talk. And yeah, if you guys don't have any questions, you can go now. Have a good day.